Hello everyone and welcome back to the Intro to C course MCS 1142. Today is week 7B, which is July 1st of summer 2021. And today, according to the syllabus, we will go over chapter 7, which is pointers. This chapter should have been split into 2 sessions, but due to an emergency in our county, we had a severe heavy rainstorm that flooded the area. So we got that emergency event. I'm gonna combine both sessions into one. As long as we cover all the topics, no matter how much time it takes, then we should be good. The topics we need to go over are defining a pointer, what is a pointer, and how to declare a pointer, how to initialize a pointer, how to dereference a pointer, how to pass a pointer to a function, how to use constant pointers or constant pointers to variables. We're going to go over also arithmetics with pointers. We're going to go over the relation between pointers and arrays. And finally, we're going to go over homework 7 if we have more time. So with that being said, what is a pointer? Let me type the definition here. What is a pointer? So if you get asked, a pointer is a variable. It's always a variable. It's not an address. It's not a memory. It's a variable just like any other variables that you declare. But the only difference is that pointer carries a memory address as its value. So when you declare an integer value, when you declare an integer variable, that integer variable will carry an integer value. When you declare a character variable, that character variable will carry a character value. In this case, a pointer will carry a memory address in it. Remember that hexadecimal value we used to see? That hexadecimal will be carried by a pointer variable. The variable will have the value as a hexadecimal, which is the address of another variable. And we're going to see that in demonstration. So this address, this variable will carry a memory address, and that address would be the address of another variables. Now, why we are learning about pointers? Because pointers are a powerful feature in C language and could be maybe the most difficult capability in the language to master. Like if you want to master all the topics in C language, pointers would be the most difficult topic. Why they are most difficult and why they are powerful? Because they can accomplish many tasks at the same time. For example, they can pass by reference. At the same time, they can pass functions between functions. For example, you call a function and you give it a pointer to another function, for just like the boss and the worker example. So you, a method would be the boss. For example, main is the boss. It will call another worker function and will give it a pointer to another worker, just like you're saying, hey worker A, here is worker X, take him with you and do that task. So you're passing a function between other functions. Also, power pointers can create and manipulate dynamic structures. Remember with arrays, we said they have to be fixed in size. So arrays must be fixed inside, but with pointers, you can have dynamic structure. For example, you can ask the user, hey, how many students would you like? Or how many grades, or how many numbers, or how many items? And then the user says 6, and then you dynamically in runtime, instead of compilation time, in runtime, you construct and allocate memory for only 6 items. In arrays, we've seen fixed size where you allocate 100 initially or at compilation time, and then throughout the runtime, you add a sentinel, you add a -1, which will identify the end of the data, right? So pointers have many capabilities, but you're not going to learn all of them in one session, not in this course. So how do I declare a pointer and how do I initialize a pointer? So before we start, I'm gonna just type the basic. For example, I'm gonna say int count equals 7, and then I'm gonna declare a pointer which is int asterisk count ptr, means the pointer of the counter. In this case, I'm gonna say equal ampersand count. What I'm saying here is I'm saying declare a variable of type integer and assign 7 as the value. Then I'm declaring a pointer. Int asterisk means a pointer to an integer, which is, this is what it's called, this is its name, count pointer. And then I'm assigning it the memory address of count. By adding the ampersand in front of the variable means I'm dereferencing, I'm actually referencing that variable. I'm grabbing a reference of that variable, which is the memory address of that variable, and assigning it into my pointer variable. Now, this pointer variable lives in the memory as well. So somewhere else in the memory, we have this pointer that is stored in that slot. Inside that slot, we have the address of this count. So if I wanna draw it, so I declared a count. I declared a count which is in this slot. Now imagine this slot is at address 6,000, for example. Let's say this count, which is here, is at address 6,000. Inside that count, I have the variable 7. I have the variable 7. So int count, variable 7, value 7 is at this address. Then I created a pointer which lives somewhere else. Let's say this will live in 7001A. This is the address of this. Now, this is count pointer, count, ptr, lives somewhere else. Now, the value of this counter is 6,000. 6,000. And just like I can reassign count, I can give it a different value. I can give count pointer different value as well. At this point, I'm giving it the address of count. At some point, I'm gonna give it an address to a different a variable. As long as all variables are an int. Why? Because count pointer is a pointer to an int. I can't assign a character address to an int pointer. So int pointers point to integers. Character pointers point to characters. Double pointers point to doubles, etc. So the object you are pointing at must be of the same type. If this is declared as a pointer to an integer, then you can only put addresses of integers, and we're gonna see why later. So this is the basic idea. Counter pointer is a pointer pointing to another variable in memory. So this is how you declare and initialize a variable. Now, what you need to know also is how to, from count pointer, how can I access count? How can I access count? How can I get the value? How can I reassign count? Why pointers are very important? Because pointers have fixed size. No matter what the address is, right? No matter what the address is, no matter what the count pointer is pointing to, whether it's this address or another address, all addresses are of the same value. Remember the hexadecimal? I have, for example, 64-bit system. So 64-bit system means I have memory from 0-bit up to all the bits are full. That means 2 to the power 64. So whatever the value is, whether it's 0 or 1 or 1 million, whatever the address is, or FAD13F, whatever the value is, it's going to be 64 digits or 64 bits, which is the size of it. So whatever the address is, it's gonna be the same it's the same size. If this address evaluates to 0, it's going to be 64 numbers. All 64 are going to be zeros, so they evaluate to 0. If a 64 bit representation evaluates to 1 million, it's going to have the same size as well, 64. If this 64-bit representation evaluates to this address, it is 64-bit representation. So whatever the value of the address is, it's going to be of the same size. So whatever you are pointing to, whether it's a count or an array or, it's going to be the same size. You are always allocating 64 bits, which is 8 bytes. You are always allocating 8 bytes, whether you are pointing to 1 byte or 10 megabytes file or 1 gigabyte hard disk. You're always pointing to the beginning address. So when you are passing by functions, when you are passing variables between functions, by default, you're passing a copy of the variable. So if you're passing a file, for example, that is 10 megabytes, you're always by default passing a copy of the file. So if you call that function in your program 100 times, then it's 100 times 10. Your program is eating the memory. Now, if you use pointers, no matter what you are pointing to, you are always passing 8 bytes between functions. If you call it 10 times, then it's 10 times 8 bytes instead of 10 times 10 megabytes, right? So this is the idea. So that's why pointers are useful, because they are lightweight. No matter what you are working with, no matter what you are pointing to, you're always working with the pointer to it, which is lightweight. You can pass it between functions and it's going to be speed. It's going to gain you speed. Now, with that being said, I'm not going to care about count. I would like to access count from my pointer. Let's say somewhere else in the code, I want to work with counter pointer, or I want to pass it to another function, and that function received a pointer to an integer. How do I access the value? Hey, pointer, you are pointing to an integer. What's the value of that integer? The way you do it is called dereferencing, which is like this. So I'm going to say print count ptr is pointing to a variable that has the value of this. And then what I do is asterisk count ptr. This way, I'm dereferencing the counter. Count pointer as is a memory address, right? By adding asterisk behind it, that means I'm dereferencing it. That means give me the value that you are pointing to. So if I run, it's going to display the number 7 because I'm dereferencing it, 7. Now, if I don't put the asterisk and I run it, it's going to be the pointer. Well, it's now negative decimal because I told it to display a decimal. Hexadecimal is X. Yep, so this is the address. So if I go and I stop here and I run again, before I display, I'm going to hover my mouse. Look at the value. It's 00006EA18 da da da. So counter pointer is carrying this value. Now Visual Studio is showing me 7 because 7 is at that address. Count is 7. If I grab this and I say add watch, it's going to show me the address. Why? Because count with the ampersand is referencing count. So here I'm referencing count, means give me the reference to count, means give me the memory address of count, and I'm assigning it to count pointer. And then I'm dereferencing it, means hey address, do the opposite of what you did. So from a variable, from a value, I grab the address, right? From a variable, I grab the address. Here, I'm doing the opposite. From a pointer, give me the value. And I do that by adding an asterisk. But for now, what I wanted to show you is this is 6EA. So if I continue, it's going to display 6EA. Did I need to add 2 X's to show the entire thing? So counter pointer is, oh, here, I want this. Add watch. So it is 50B73. Why I'm showing this? Yeah, but I need to display more than 8. Is it because I'm building? Anyway, you get the idea. I don't want to waste time on this. Watch. So it ends with 574, 574, continue. 574, but it's displaying everything. Hold on. Display entire hexadecimal value in C language. Yeah, this is part of being a programmer. You don't like something to stop you. Let's try that. No, this I want to display, for example, 10 or 15, because I think it's 16 right now. Go. No. 10. Go. I didn't display everything. Anyway, so I'm displaying the address. If I say dereference it as a decimal, then it's 7, which is count. So this is how you access the value that the pointer is pointing to, whether it's a character or. If it's an object, you grab the object and then you access that object, and you're going to learn that in the future courses. Next, I want to show you how to pass by pointer. So let's say I'm going to type. I'm going to have a function that is called void. It returns a void, and it's called cube by reference. Right? I wanna multiply 3 times the number by itself 3 times, but I'm gonna pass it as a reference. So int asterisk my APTR, which is an argument. What do I do with APTR? What I do with APTR is I'm gonna say whatever APTR is pointing to, I wanna reassign it a value, and that value would be whatever APTR is pointing to multiplied by whatever APTR is pointing to multiplied by whatever APTR is pointing to. So what I'm doing is go back here. Count is 7, right? And I'm passing the address. I'm passing the address for the function. So a function will receive the address 6,000 as an input. And then what I'm doing is, hey, go to the address 6,000 and assign a value in it. So this is the memory address in 6,000. And I'm gonna assign a value to it. So here, I'm gonna assign into it. What I'm going to assign into it, I'm going to assign whatever the memory address 6000 containing. So 6000 at this point contains 7. This is 6000 multiplied by also 6000, also 6000. So when this statement finishes executing, it's gonna grab the value of this 7 times 7 times 7 and assign it to the address 67. So it will become 7 times 7 times 7. And then it will be done. So even if this function finished executing, the address at 6000 has been changed. So the boss function, or in this case main, is gonna go access 6000 and it will no longer find 7. Why? Because another function changed the value in that memory address. So it's the same behavior exactly like passing by reference. Whatever changes you do in this method, the caller method will know about the changes. So notice, here's what I'm doing here, correct? And then I have count pointer, and then I'm gonna say first I'm gonna print existing address. So count is now D, and I'm gonna dereference count pointer. So I'm gonna go to the address of count and display the value that is inside it. Then I'm gonna say cube by reference. I'm gonna pass it counter pointer. So I pass that address, or this is equivalent to saying pass the reference of count. So passing this or this are the same. Why? Because this is equal to this here. This is equal to this. So if I pass the pointer or I pass the reference of count, it's the same thing. Once I'm done, I'm gonna do the same thing. I'm gonna display, which is the same as this. Dereferencing this is the same as doing this. Dereferencing 6000 is the same as, hey, show me your value. So now if I run count pointer display, it's gonna display 7. Then I wanna add a new line here, and then F10, F11, I mean, sorry. So a pointer is pointing to this address, which has the 7. So I'm grabbing 7, multiply by 7, multiply by 7, and assigning it to that address, which is 00647. So instead of the 6000, we have 47C, F5B, F984. So go. Now it's cubed. It has been cubed. Now this memory address in my system has the value 343, which is 7 minus 7 times 7, 343. So continue. Now I'm back here. If I hover my mouse at count, it's 343. So whatever changes happen in this method, main knows about it. So we passed it by a pointer is the same behavior as passing by reference. We didn't give that method a copy of the value. We gave it the memory address. It's like giving you the same key to that mailbox instead of giving you a copy of that mailbox somewhere else. There is a mailbox that has some value, and I gave you the key of that mailbox instead of copying the mailbox and giving you a copy of the mailbox, and then you can do whatever you want with it. With that being said, I'm gonna continue, and then clock count is 343. So this is demonstrating pass by pointer. Now, another thing you need to know is you have 4 ways of declaring pointer and assigning it a value, which is, for example, right now, I was able to change the value in that memory address, right? We have the memory address 6000, and I was able to change it from 7 to whatever I want. In this case, it was 343. That means I have a pointer that is pointing to a variable which is not constant. I can reassign it. At the same time, I can reassign this. For example, this time I gave it the address of count. Somewhere else in code, I might have count 2, which is 10, and then I can say count pointer is now the address of count 2. So now it's no longer 6000. Let's say this variable was created at address 8000A. This address was created at 6000. So now, sorry, excuse me. Ooh, sorry. So at this point, before this gets executed, count pointer had the value 6000 in it. When I reassigned it a value, now instead of 6000, now it has 8008. So I created a variable pointer to a variable variable. Bear with me, to a variable variable. What I mean by a variable variable means I can say count PTR equal to 20. So not just count pointer was reassigned, also count 2 was reassigned. Count 2 started as 10. I gave the address to count pointer, and then I dereferenced counter. I said, hey, counter pointer, whatever the value you are pointing to, I want to trigger it. I want to change it from 10 to 20. So this is the first type of declaring a pointers, which is a variable pointer to a variable. You can call it variable or you can call it value. And this is the first type. So types of declaring a pointer. So one is a variable pointer to a variable value, which is this case. Yep. So let me start here. You have var ptr to var value. This is 1. 2, you have var pointer to a constant value. 3 is a constant ptr to a variable value. 4 is const ptr to const value. So this is what you've seen so far. We were able to create a pointer and give it another address. And inside that address, we were able to change that value. So it's a variable value. It's not a fixed or constant value. It was variable. So it was able to be modified. Another type is creating a variable pointer, but it points to a const value, means this pointer can point to one variable this time, can point to another variable next time, can point to a third variable next time, but you cannot dereference it and change the value. Why? Because it's pointing to a const. That value is constant. You cannot change it. You cannot dereference that pointer and change the value. The third type is constant pointer, but to a variable value. Means you create a pointer that points to a variable, for example, count. But if you create another variable, count2, and try to put the address of count2 in your pointer, it's not going to allow you because this pointer is constant. This pointer can carry one address and one address only. It cannot be reassigned. It can't carry a different address. Now you can dereference this address and change the value. That's fine because it's pointing to a variable value. The last case is both are constant. You create a variable count and then you create a pointer to that count. Both the pointer cannot be reassigned a different address, and you cannot dereference that pointer and change the value. Both are constant. The pointer is constant and the value that is pointing to is constant. Now, how do we implement this? How do we implement this? And you better take notes. So one is that, two is, what did we say to? Two, we said var to const. So a variable pointer to a constant value. The third is a constant pointer to a variable value. Four is a constant to constant pointer to a constant value. Now, how do I do a variable pointer to a variable value, which is the first case we saw? So I say int count equal 10, and then int my or count ptr equal the address of count. So this is the first way. How do I declare a variable pointer to a constant value? I say I want a const int pointer, or basically first int count 2 equal 20 for 2, 10 for 1. So I want const int pointer count ptr count 2 ptr equal the address of count. Take notes. Okay, so you see how I said int count 2 equal 20. If I say const int count 2 equal 20, that means count 2 cannot be modified anymore. Why? Because it's const. Count 2 equals 30, for example. It's going to say, no, you can't do that because it was declared as const. Expression, what it says, expression must be a modifiable value. L value means local value. You don't have to worry what is meant by a L value. So you see how I create a constant variable? I add the word const. In this case, I said I want a const int, means pointing to a const, and it's a pointer. So it's a pointer pointing to a const integer. And you can have a space here, that's fine, or here. The third way is a constant pointer to a variable value, means I would like a int, right, pointer, but it's a constant pointer. First, let's create the count 3 equals 30 for 3, and then I want int pointer that is const, and I'm gonna call it pointer 3 equals the address of count 3. So here I'm saying I would like a constant pointer. So constant pointer from right, if you want a good way to remember, because that's how I remembered it as a student. I always read the declaration from right to left. So it's a constant pointer to a variable value. In this case, it's a variable pointer to a constant integer. Okay, you split, just a split at integer, whatever comes on the right pointing to whatever comes to the left. And the last case was const to const. So just add bunch of consts. So let me say count 4 equal 40 for 4. And then this is a const. And then it's a const int pointer const count 4 ptr equal whatever the address of count 4. Now, these are the 4 ways. If you wanna take a print screen, pause now and take a print screen. 1, 2, 3, 4. Now notice for the first, well, we demonstrated the first one. Notice in the second one, it's a variable pointer to a const value. That means I can give my pointer a new address. So I can say int count 10 equal 100. And then I can say, hey, count2 pointer, I would like to give you a new address. And that's fine because it's a variable pointer. However, I cannot dereference that pointer and change the value. It's not going to allow me like 100, 200. It's not going to allow me. It's going to say this is a constant value. Whatever you're trying to dereference, whatever you're trying to change is a const, is declared as a const, so you cannot have it. This pointer is pointing to a constant integer, so you cannot change it. So it's an error. It doesn't compile. You see how it doesn't allow me? Now, in this case, it's a constant to a variable. That means since it's a variable value, means I can dereference it and change the value. For example, I can change the value to be 40, but I cannot say, hey, count3 pointer, I would like you to have a new address. In this case, it's the variable from above. And it's not going to allow me. It says, hey, this is a constant pointer. It's a constant pointer pointing to a variable value. Means, okay, it's fine to dereference it and change the value. It's fine to have access to the value that this pointer is pointing to, but you cannot give the pointer a new address. You can't. This must be a modifiable value. Notice it doesn't allow me. Now with const and const, I can dereference and change. I cannot dereference and change for PTR equal 1000. I cannot do that. And I also cannot give it a new address. So if I say count for PTR equal the address of count 100 from above, it doesn't work. Count 10. It doesn't work. It says, hey, this is constant, and you're trying to reassign it a new address. And at the same time, hey, this is pointing to a constant, so you cannot change the value that this pointer is pointing to. These are 4 different, and every type has a use case. There are many use cases that you need to have a const pointer to const value or this or that. For example, for safety, for security, as a matter of fact, for safety or security. For example, if a method's job is to display, if it's just a display, that means you shouldn't give it access to change the value. If a method is just to display, then you give it a constant pointer to a constant value. This way, if another developer is implementing the print function, you are not giving that person the access to change the data. If his job is to just display, then here, just display. It doesn't matter. It doesn't mean he's gonna change the values on purpose. It can be by mistake. You know, in code he did a mistake and he's changing the values. So in order to cover your back, in order to save time, in order to secure the code, if a method's job is to just use the data, then you don't give it access. Just don't give it access. If its a job is to just use the data, then here, use the data, but you're not allowed to change it. And many more based on the use case. You're gonna figure out, hey, is this let me give him a variable pointer to a constant value. It could be variable pointer to a constant value. When did I use that? I don't remember from top of my head really, but once you start once you open your scope and act like this work and be like, I'm receiving this. This is gonna go da, 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 da. Okay, then this should be constant to variable. You're gonna figure it out right away as long as you understand the concept. Cool, cool. Next thing you need to know is arithmetics with pointers, because you can do arithmetics. Arithmetics, I mean, you can increment, decrement, you can add one, you can add two, but it's different. It's different than adding one to an integer. I'm gonna remove this now. For example, let's take this example. Let's say we have a string, right? An array of characters. And we're gonna pass that array to the array of characters to a method, and that method will convert all lowercase to uppercase. Okay, so let's say I want a char array and it's called my string. It's of this size. The fact that I'm assigning it right away, that means I don't have it. I don't have to give it a size right away. I can say my name, small, capital, small, capital, small, capital, space, small, capital, small, capital, small, capital, small, capital, small. Boom. Then I'm gonna say, print it first. Print it for me. Printf. The string is my str. Yep. And then I'm gonna say a method, a worker, convert, and I'm gonna give it my str. Convert, call it my convert. Then I'm gonna print it again. And here you're gonna learn the relation between arrays and pointers. Remember when we said the name of the array is the address of the first item, and here you're gonna see it in action. And the fact that this is a C string, that means there is a null at the end. So the size of my str as a string is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 13 characters plus the null terminator. So my convert, and then I'm displaying. So what does my convert do? My convert is a void, and it takes, in this case, it takes a char pointer, right? It's not an integer, it's a char. What do I do in that char? I'm gonna say the fact that C string is terminated by a null. So I'm gonna say while dereferencing my pointer, my PTR is not the null character. See what I'm saying? I'm saying while so this is an address, right? This is the address of the first item. So I'm telling my worker, I'm saying, hey, if that item, whatever you're pointing to, if that item is not null, keep going. Means if the first item is null, don't go. If the first item is not null, go. So the first item is not null because it's a K, it will execute. Then I need to jump to the next item. How do I do that? I do that by saying aptr plus plus. So this will add one, yes, and it happened that it's a character array and characters are 1 byte, but I'm gonna draw it again with integers, but stay here for now. So on each iteration means on each character, if it's a capital letter, I'm gonna convert it to a small letter, or the opposite. If it's a small letter, I'm gonna convert it to an upper case. So if this address is pointing to a character that is small a small case, I'm gonna convert it and assign it to itself as well, to the same address. So to upper is from include type. Type, was it type or C type? C type, C type. So to upper, whatever the dereferenced value. So whatever the address is, dereference it means grab the value. In the first run, it's K. So pass K to upper, and then this method will return K capital letter cost to uppercase. And then I'm putting it in the same address. So I'm dereferencing the pointer, telling it, hey, what's the address you're pointing to? Here is a new value. Then I am incrementing. Boom. By incrementing, adding one means not add one as a value, not add one like 10, now it's 11, and then it's 12, because this is not decimal. This is hexadecimal, and not just that, it's a character address. Now it happened that characters are 1 byte. So what's going to happen in the memory is this. I have all these slots. Boom, 2, 3. So I have all these slots. Right? And this address would be, let's say 1000. Then this is 1, 1. Why? Because characters are 1 bytes. 1, 2, 3, 4, 5, 6, 7, etc. Boom, boom. So what I'm saying when I say A, P, T, R plus plus means add one, means APTR is whatever the value APTR plus 1. So APTR as the first iteration, APTR is 1000, so it's going to become 1001. Next iteration is going to be 1002. Next iteration is going to be 1. As long as the character is not null. So here I have null. So at some point, we're going to receive the address 14, and the loop will dereference the address 14 and is going to find null. Then it will break out of the loop. So if you want to see it in action, go, my string is whatever this, and it starts at this address. So instead of 1000, it is this. It is 616F4F7A8. Go F11. So get into. This is the address. Now, hey address, at this address, do you have a null? No. Okay. Go. Give me the capital letter of whatever your address. So whatever this address is pointing to, in this case, it's pointing to the letter K, because this is the address of the first item. Then I'm going to grab the capital letter of A and put it back in the same address. So when I step, it's going to become capital K. So at this address, it became capital A. So now notice with A PTR plus plus, the 8 is going to become 9. Boom, 9. See? So now the address, this APTR is pointing starting from 9 up to the null, means from H up to the null. So go, hey, at address 9, is it a null? No, it's not a null, it's an H. Okay, then do the same and jump. Now it's an A. Remember, hexadecimal is 0 to 9 and then A, B, C. So it was 8, 9, and now it's an A. Then if I go, now it's gonna become B, then it's gonna become C, then it's gonna become D, E, F, and now it's gonna become back to 0, and then the A will become B. So hey, are you pointing to a null? No, I'm pointing to okay, go, go, go. Now it's B0. So again, 1, 2, 3, 4, 5. So now 5 is the end and it is pointing to null. So it breaks out of the loop because at this address, which is the address after the last one, the address after the F is a null character because this is a C string. It breaks out, it displays, and it's gonna be all capital letter. Now I want you to have a solid understanding of this +1. And for that reason, we're gonna do it with an int. And you're gonna see what I'm talking about, what I was trying to display here. If my array was an integer array, so let's do it. I'm gonna say I want an integer array, right? And this integer array is gonna be 1, 2, 3, 4, 5, 6, 7, 10, 10, right? Oh, I'm missing 9, 9. So what's the size? The size is 10. So my convert takes an integer pointer, and the size is int a size equal 10. Remember, every time you need to pass an array integer, you either need the actual size or you need a sentinel. Sentinel based on the logic. It could be -1, it could be 9, -900, it could be 101. For example, grades cannot be greater than 100. So if your worker function sees 101, it means that's the end of the data, right? So in this case, I'm passing the size. I'm telling my worker, hey, there is this array of integers. It has 10 in it. So iterate it means go from 0, because items start at 0, up until 10, I++. And each, let me do it in a different way. Well, that's a good demonstration. On each iteration, I'm gonna just increment APTR just to show you what's happening. So iterate. I'm not changing any values. I'm not doing anything. I'm just iterating. I'm just adding 1 to pointer. And I'm gonna break here. Now let me go to my awesome drawing skills. I'm gonna keep this here because we are on the same thing. But instead of characters, those are ints. And ints are 4 bytes. So I'm gonna remove these. And then I'm gonna say this starts at 1000. And the fact that it's an int, it's 4 bytes. That means 100110. Actually, let's keep it because it's a better representation. Yep, let's keep it like this, and then remove these. Since each integer is 4 bytes, that means each integer is consuming these. Then the next integer is consuming 4, 5, 6, 7, and so on, so forth. There is no null anymore because it's not a string, it's array of integers. So each integer is consuming 4 bytes, right? 0, 1, 2, 3, done. 4, 5, 6, 7, done. 8, 9, So this has 1, and this has 2. This has 3. So 1, 2, 3, 4. This has 3, 4 bytes each. So save 0, 1, 2, 3, 4, 5. Okay, good. Now see what's happened. What's gonna happen? Well, this is not a string anymore. I don't want to display. Just pass it and show me. So I have my string. It's an integer string. 1, 2, 3, 4, 5. It starts at 48. Now F11 inside, it starts at 48. Now I'm gonna pinpoint this. So it's 48. When I add 1 to it, it's not gonna be 9. Why? Because it's an integer array and each integer is 4 bytes. The fact that each integer is 4 bytes, that means the plus 1 is not adding 1 to the value. The plus 1 means go to the next item. So notice 48 will become B. Actually, will become so 8, 9, A, B. It will become C. Boom, C. So it was at 0. The next item is not 1. The next item is 4 bytes later. So now it's pointing at the next item. So A pointer is pointing at 2 now. Then C becomes 0 and it's pointing at 3. Then the next item at 4. So 0 to 4. This is a good example because it matches. 0, it's now at 4. Then it's going to be at pointing to 4. Then it's going to point at 5, which is at 8, which is here. Boom. Because 4, 5, 6, 7, 8. Then it's going to be 9, A, B. So 8, 9, A, B. Then back to C, which is 4. So go. Boom. See, here it is. So you see plus 1, when you do arithmetics with pointers, you're not adding values to the address. When you are working with a pointer, you are jumping from an item to another item. So if it's an integer item, it's gonna jump 4 bytes. If it's a character item, it's gonna jump 1 byte. If it's a short, it's gonna jump 2 bytes. If it's a double, it's gonna jump 8 bytes, etc. So this is arithmetics. Also, you can add, you can multiply, you can subtract, you can add 2 addresses and you will get the third address. Yeah, and those are in the book. Yeah, you need to read those just to get an idea of what is arithmetics with pointers. So here I'm looking at the book. It is saying constant versus variable, etc. So we did that. And now it's arithmetics. We did that. What else do you need to know? This is passing by pointer, right? The last thing you need to learn really is what else do you need to know? Yeah, you will need to know the difference between pointer notation and index notation. Okay, pointer notation and index notation. Remember with arrays, we were displaying, for example, printf, the current item is /n, and that would be index notation. So hey array, this is my array, display the item at this index. This is called index notation. I'm giving it index. So at index 0, display this, whatever the item is. At index 1, display this, similar to if I'm doing it here. Copy, paste. Right? So I have an array that I gave it numbers, and then I'm iterating my array, and in each iteration I am displaying the current item. This is called index notation. Now, in order to understand the relation between pointers and arrays, there is a pointer notation. And once you learn about pointer relation, you're going to be surprised like, an array is an actual pointer. Wow. I didn't know that. Why? Because I can do this just like how we learned it earlier. I can dereference whatever my pointer plus X items. So if I is 0, means whatever the value, whatever the address is, plus 0 items, and then dereference it. If I is 1, that means whatever my address is, which is the starting address. Remember, the name of the array is the address of the first item. So the beginning address, the starting address. So with this notation, I'm saying, okay, the starting address plus 0 for the first iteration. That means it's the starting address. Okay, then dereference it. On the next iteration, it's going to be I equal 1. That means my starting address plus 1 item, I'm going to grab the next address, right? I'm going to grab the next address. Okay, then dereference it. On the next iteration, it's going to be the starting address plus 2 items. I'm going to get to the third address. Okay, then dereference that third address. So both this and this will display the exact same thing. One, two, three, four, five, six, seven, eight, nine. 1, 2, 3, 4, 5, 6, 7, 8. Both did the same thing. Let me step through to show you. And I'm gonna pinpoint this. Go, 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 go. Okay, so the starting address is A8. And the first iteration, I is what? I is 0. I is 0, that means I'm here. Okay, so this address plus 0 means 0 items. So this address plus 0 items means the same. I am still at the starting address. Then dereference the whole thing. So dereference the result of this, which is the first item, 1. Now on I2, that means I'm here at 2. That means, hey, whatever the starting address is plus 1 size of an item means 4 bytes. So this address plus 4 bytes will become what? C. Then dereference the whole thing. Boom. Same for 2. Starting address plus 2. Starting address plus 3. Or if you want to understand it in a different mentality, means this address plus 3 times 8, 3 times 4, sorry, because 4 bytes, right? Each integer is 4 bytes. So my starting address plus 3 times 4 is what? 12. That means A8 plus 12 slots. So A8 is 0, A9, AA, AB, 12 slots, you're going to get an address. That address would be this item, which is 4. If you keep doing this technique, you're going to figure out, you're going to realize that you are basically displaying the values in that array. And that's it for the topics that you are responsible of. Sorry. Let me think. You need to know about bubble sort. It's a code in the book that you need to know how bubble sort works. Bubble sort is basically called bubble because if you have an array, boom, 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 that is not sorted. So let's say this has 3, 1, 5, 2, 0, 10, 9. As a human being, if you want to sort this, how do you sort it? There are many ways, right? There is insertion sort, like you sort a cards. Insertion sort means you look up the biggest number, and then you insert that biggest number in its slot. For example, 10 should be inserted here at the end. Once you do that, then you go over it again and you pick the next largest one. 9, it should be inserted here. The fact that this got swapped at the beginning means you're good. Then you go to the next largest. What is the next largest? 5. Okay, then 5 needs to be inserted here. So you swap. You basically insert, not swap. So you remove the 5 from here, insert it here, and then you shift these two to the left. You keep doing that. That's a sort. There's another sort. There's a lot of sorts, many sorts. I don't know if you can hear it, hear like the sound from my computer, but there is this cool video which is algorithm sorting algorithms visualized. These are only 15 sorting algorithms in 6 minutes. So let me increase, let me go, and it should tell you. So for example, this, I don't know if you see it here, but you should see it when you play the video. Just go on YouTube and Google visualize sorting algorithm. So this line is gonna tell you what the name of the algorithm, how many comparisons has been done so far, and how many times the array access has been. And then there is one more, which is, I think, I don't see it because there is this menu for Zoom popping up every time I hold my mouse. But you see these comparisons and accesses. This is um, what classifies or qualifies an algorithm, whether it's a good or bad algorithm, whether it's fast or slow, whether it's complicated or simple. The number an algorithm, so the number of comparisons and array accesses and this and that an algorithm does is what clarifies that algorithm to be slow or fast. So selection sort, if I start from the beginning, notice all these are random. So it's shuffled array. And selection sort is gonna sort it. Selection sort is gonna select, like that's why it's called selection. It selects a number and then swap it between another selection. I think the tone you're gonna hear is the array access. So how many times you're gonna hear two tones throughout the video. One tone is for array accesses and another tone for comparisons. So if you hear a lot of tones, that means a lot of comparisons are being done and a lot of accesses are being done. So let's play. So it sorted it. If I play speed at this very slow, you can get an idea of how it works. Selection sort will go select if there is descending and ascending, remember? So if you're sorting in ascending, so selection sort is gonna go pick them. So it's gonna go from all the left to the right. So linearly through the entire data set. It's gonna go and pick up the minimum. Which one is the minimum? It's gonna grab it, select it. It's gonna select the minimum and put it at the beginning. Then it's gonna do the same for the entire array. So look, so you see the red, it goes over from left to right. And while it's going, it's gonna mark the minimum so far. So right now the algorithm is at this section and it marked this as the minimum so far, and it will continue. It happened that I paused it at the minimum so far and there is no other minimum. So it's gonna grab this and push it to the far left. Now in the next iteration, see, it's grabbing other minimums. So it's sorting. I'm gonna go back to normal. That's selection sort. For it to sort, it took 7875 comparisons and 15,526 array accesses and one more, which I can't screen. Oh, okay. So which is a delay. Okay, so they delayed it just so you can see it. Another sorting algorithm, insertion sort, insertion. So insert, grab, insert, etc. So let's slow it down. So insert. Notice that it is a difference between this and the previous one. The previous one was going from left all the way to the far right every iteration. So every iteration, the previous ones, the selection sort, on every iteration, it goes through the entire data set. And in that iteration, it marks the minimum so far. And once it reaches the end of the data, it grabs that minimum so far and swaps it with whatever index we are working on. In this case, it's not going through the entire set. It's going, for example, it is at green right now. So when it goes to the next iteration, it's gonna grab this and insert it in its place within this section without going for the entire data set. So at each iteration, it's gonna grab the current item and go over the previous data and see where should I put this item here. Okay, next data. Where should this next data go? This is similar to deck of cards. When you are playing cards and you take, let's say, 13 cards, the way you sort your cards are insertion. You go look at the cards and then start from left. Where should the very first item will stay in place? Then the next item. Where should the next item go in comparison to the left section? Then you insert it. Then you go to the next item, you insert it to the left. You go to the next item in the right, then you insert it in the left. I'm gonna go again. So you see, it's grabbing items and inserting it. Grabbing items from the right, inserting it here. Once this is done, it's gonna say, 17,119 comparison 15. So you see the difference between how many times this did with respect to the previous one. Another one is quick sort. This is what I was about to speak about. Quick sort. No, sorry, I was about to speak about bubble sort. So you can play with this video. You can see all of them. This is merge sort. It merges lists. It sorts small lists and then merges them. This is called heap sort, which is very fast. This is radix sort. This is standard sort. Stable sort. Shell sort. Bubble sort. Bubble sort will, just how I said, it will go over the list, it will grab the maximum and then will put it to the right. Go over the entire list, grab the maximum and put it to the right. That's why it's called bubble, because the biggest number from your data set will bubble to the top. It will go grab the biggest one and the biggest one will bubble to the right. Like bubbles go in water, you know how bubbles go from bottom to top. So that's why it's called bubble sort. Now, once if you like this topic and you want to go in deep with it, you're gonna learn that there's no best algorithm. Some algorithms are good in one thing, another algorithm are good in a different thing. Some algorithms are good for partial shuffled. Some algorithms are good for completely shuffled. Some algorithms are good on small data. Some algorithms are good on big data. So if an algorithm is good on 100 items, it might be very bad on 1,000 items, and the opposite. Some algorithms are very slow if it is only 100 items. Why? Because the way they work, uh, it you basically are how do you say it? You are putting additional work or extra work on a small items, on small number of items. The algorithm will be sophisticated and will work in a technique that is good on large data, not small data, and so on and so forth. Why sorting is good? Why sorting is important? Well, it's important for many reasons. Because you probably use sort like 100 times a day without you noticing. For example, if I go to Google and I say cars around the world, right? When I do that, I receive, look how many, 1,670,000,000 results in this time. And you know these all these results are sorted. What's the criteria? The criteria is most relevant first. Most relevant first, or most or best match first, and then the least match, right? Then the least match, then the least match, then the least. So Google was so fast that not just so Google didn't just get me 1,600,000,000 results only, but sorted as well. So that's why sorting algorithms should be fast, because for the user it has to be fast service, right? And let's say I want to sort, these came up sorted. Maybe they were, you're going to say, maybe they were sorted already in the database. Well, no, they weren't sorted already. You know why? Because I can control that as a user. I can say, I want in the past 24 hours, boom, and I want, oh, there is better, there is more tools. Hold on. Well, let's go to Amazon. Let's go to Amazon, and I'm going to say motorcycle phone mount, right? Motorcycle phone mounts. Sort. So it didn't just get me 1,000 results in a second. It also sorted them by featured first. So most relevant first, and then all the way to the rest. Then I can sort again. I can say, okay, well, sort by price. So now it is 5,000 and sorted lowest first, then. So it was sorted. Which sorting algorithm did Amazon use? We don't know. It depends. It depends on the data item. It depends of if those results were partially shuffled or completely shuffled in the database. In their database, were those results completely shuffled or partially shuffled? Because some algorithms are good for partially shuffled. Some algorithms are good for completely shuffled, and so on and so forth. So that was the idea. Please go over the book and learn about bubble sort. I need you to learn about bubble sort. You are responsible for bubble sort. And let me know if you need any questions.